Hello, this is Satish Kumar, and today I'm presenting our work titled Unsupervised Activity Segmentation by Segmentation Learning in Online Clustering. This work is partly funded by NASA's Human Research Program. Do you have video datasets of semi-repetitive activities such as surgical rooms, warehouses, factory line assembly, gyms, sports, or kitchens? Insights extracted from these datasets could be used for guiding manufacturing workers, standardizing surgical rooms, as well as optimizing warehouse processes, amongst other applications. Unfortunately, training deep neural networks for visual activity segmentation requires costly frame-wise labels as supervisory signal. Our goal here is to train activity segmentation models in an unsupervised manner. These models could be used for localization of salient actions, autonomous discovery of task structure, as well as video summarization. On your left, you can see our approach in action, where the original video is at the top and the segmentation predicted by our approach, along with the ground truth names, are visualized at the bottom. Previous approaches for unsupervised activity segmentation often treat representation learning and clustering as disjoint steps. They first learn representations using a pretext task and compute the representations for the entire dataset. These representations are then passed to an offline clustering module to obtain the final activity segmentation. The downsides of such approaches are twofold. First, they require the entire dataset in memory to perform offline clustering. Second, there's no feedback between the representation learning and offline clustering modules, which may lead to incoherent clusters. We, however, combine representation learning and clustering into a single joint framework. We process a small batch of frames at a time and simultaneously perform representation learning and online clustering. This not only leads to improved performance but utilizes much less memory. Further, it yields consistent clusters due to feedback between the representation learning and online clustering modules. For each training iteration, we first sample a small batch of frame level features and pass them through a two-layer encoder network to obtain the embedded features C. These features are then passed to the temporal coherence loss. This loss encourages temporally coherent representations, that is, neighboring video frames are mapped to nearby points in the embedding space and vice versa. To perform online clustering, we also learn a set of prototype vectors which act as cluster centroids, denoted here as C. Each of these prototype vectors represents a step or class in the activity. To obtain the predicted cluster assignments, we compute the vector similarity between the prototype vectors and the features. This gives us the probability of each frame belonging to a particular cluster. The prototype vectors and the features are also passed to the temporal optimal transport module. Since there's no explicit supervision for training the network, we propose temporal optimal transport to obtain pseudo-label cluster assignments referred here as Q. Specifically, we impose two constraints on Q. First, each cluster centroid must reassign an equal number of frames, and second, the temporal ordering of the clusters must be preserved. This is an instance of the classic optimal transport problem with vector dissimilarity between the prototypes and the feature vectors as the cost metrics. Finally, we minimize the difference between the predicted cluster assignments and the pseudo-label cluster assignments using the cross-entropy loss. Our approach achieves significant gains in performance over previous state-of-the-art methods while being 3 orders of magnitude more memory efficient. We demonstrate the performance of our approach on a complex industrial dataset with 30 steps. At the bottom left, we show the segmentation generated by our approach, where color represents a distinct step in the activity. The red arrow shows the temporal location of the current frame in the segmentation. We also show the name of the step as it corresponds to the ground truth segmentation labels. Notice that our approach does not utilize these segmentation labels, but we visualize them here just to facilitate understanding. We also show the boundary frames extracted by our approach. Each of these frames corresponds to the start of a new step in the activity. Notice how there are very subtle visual differences between each step in the activity, yet our approach reliably segments out several key steps, including attach the glass on the keypad window, attach one thermal pad on the housing, as well as get keypad board and remove all connections. Please refer to our poster as well as full paper on archive for more details. Thank you for listening.